Hey everyone, Chang here and welcome to my channel. Now, while I was looking up like math competition, math puzzle type problem, just online, in books, whatsoever, I started to realize there's actually a specific subset of problems known as warm-up problems. Now, that baffled me because, the only time I really ever hear warm-up is basically in fitness or in exercise in general, right? You want to warm up, prime your muscle, have blood flowing, be a little more flexible or whatsoever to make sure that you avoid injuries. Well, unless you want to say mental injury just because, math is sometimes a little mean, you force you to think of ways that you really don't want, right? It makes kind of not much sense to have a math warm-up. But as I look in it a little further, okay, I can give it that. So sometimes, we just came out of a class, maybe English class or philosophy. We're just not in the right mindset to really be thinking about how to solve and approach math problem. So if you have specifically math problem designed to sort of get the blood flowing, right, to think about it in a way, then I guess it would work. So I went and I looked and I picked some of these math problems just because I like how it really does prime you to think about the concept more than anything, right? There's no really hardcore any computation, but it's one of those like, all right, when I first look at this problem, maybe I can't come up with the answer right away. Maybe I have to sit on it, slowly brew on it. And eventually, once you do maybe like a couple of these problems, it's like, all right, now I'm in the correct mindset to be solving math problems. Now I can instantly think of different ways. Not guaranteed to find the answer, but at least, be more inclined to approach it in a more mathematical or logical sense. So let's look at the first problem that I found that I thought was absolutely amazing. It's designed to look super complicated. And of course, if we're slowly warming up, we might not see how to do this problem right away. Now, the problem is quite simple. You have 4 times the square root, which makes it a little scary, and all of a sudden you have 3 things inside the square root. You have x minus 1, you have x minus 2, and you have x minus 3, plus 4 equals 4. Now, I've seen 2 variations of these kind of problems. The first one is just basically, what the heck is x? Right? The second one is even crazier. It was like the sum of all numbers that makes this statement true. Makes this true. Okay? They're basically the same thing. One is just one more step. Now, if we think about x, oh my God, how do we solve this? Well, as we start thinking about it and looking at the actual problem itself, well, imagine if I'm just trying to solve for x. The first thing I would do is get rid of all the numbers and all the, stuff that's messing with x. Well, the first thing I would do is get rid of 4. So I'm going to subtract 4 on both sides. Then all of a sudden, the next thing I know, the problem itself became quite simple. X minus 1, x minus 2, times x minus 3. But since I moved the 4 and they cancel each other out, it's 0. 4 times the square root of some number equals 0. Guess what? Doesn't matter about the 4 because any number times the square root of whatever number, if it ends up being 0, is great. So we need this thing to become 0. Well, here's the thing, right? No matter what, this is a multiplication of technically 3 numbers. Multiplying by any number is fine, but multiplying by 3 numbers, that means one of those numbers must be 0, right? That's the only way you can get 0 if you're doing multiplication. One of the number. It could be all, but at least one of them had to be 0. So in this case, in order to find x such that this statement is true, right, figure out what it is, all we have to do is find x such that this square root ends up being 0. So 4 times square root of 0. Square root of 0 is 0, so it's 4 times 0 equals 0. So each one of them, what number would cause it to be 0? Let's look at the first one. X minus 1. Well, if x is, guess what? 1, this would be 0. Okay, let's look at the second one. Ignoring whatever this could become. The second one, what number must x be to make this second number 0? Well, 2, right? Because 2 minus 2 would be 0. The third one, same reasoning. 3. And just like that, we solve this problem, right? X equals, well, 1 or 2 or 3. Any of these 3 possibilities. Now, the sum of all numbers that make this basically statement true, simple. 1 plus 2 plus 3, 6. And just like that, right? A very complicated problem that if we're not primed to think about it and try to figure out what it's asking, it seems scary. We don't know what to do. But then once we're warm up, we got it. Now, this next problem is actually quite interesting. Now, it's based on two concepts, and I've underlined them right here. The greatest prime factor and least common multiple. Now, if you've never heard of these two concepts, then yeah, encountering this problem is not going to be all that helpful. It's not going to warm you up. You're basically screwed, right? Now, if you're not comfortable with it, I do have videos on these, so I'm going to put a link in the description down below. But other than that, the greatest prime factor and the least common multiple. If we know them, we basically now have to understand the problem. And then once we understand it, we realize actually it's not much computation. It's just using the general definition and the theory behind these two to understand and solve the problem. Let's see. The greatest prime factor of the least common multiple of 21, 24, and 60. First and foremost, least common multiple of 21, 24, and 60, meaning that whatever number we find is the smallest number such that it is divisible by these three numbers. So that number is going to be divisible by 21, it's going to be divisible by 24, and it's going to be divisible by 60. Now, from that number, we want to find the greatest prime factor. So we're going to get that number, we're going to break it all down into its prime factors, and then we're going to choose the biggest one. Now, here's the key though. In order to find the least common multiple, right, the surefire way to find the least common multiple of any number, not just these guys, but any number, you first have to break it down, all these numbers, into their prime factors, right? Then you get all the prime factors, ignoring all the, I guess you could say the, what do you call it, the repeating prime factors, right? And then you multiply them together. That's gonna be your least common multiple. Well, once we broke down all the different prime factors, guess what? We look at the biggest one, and that is our greatest prime factor. We don't actually have to figure out what that number is, right? We don't need the number that is actually divisible by these three. We just need to look at the prime factors and figure it out. So let me just show you really quickly. First and foremost, let's look at 21. Okay, if we break it down into its prime factors, that's 7 and 3. Okay, 24. Now, there's definitely many approaches to going about this, right? Some would be 12 and 2, some would be 6 and 4. And then afterwards, you start breaking down further. That's going to be 6 and 2, and this one's going to be 3 and 2. Okay, cool. Now, the next one, 60. Let's do it right here. And then we can break it down, of course, to, let's do 3, 20. That's going to be 4, 5. That's going to be 2, 2. Now, if this problem is slightly different, it's actually asking for the number. What you would do to find the least common multiple would be to find out of all these prime factor, what are the different ones? 7, 3, and then there's another 3, doesn't matter. 2, there's other 2s, doesn't matter. And 5. If you multiply all of these guys, you would get that number. But since the problem is not actually asking for that number, it's just asking for the greatest prime factor of it, we just look at all the prime factor that we just found, right? Knowing that we're just going to have to multiply these guys to get that number, we don't actually have to multiply them. What's the biggest one? 7. Just like that, this problem is solved. No heavy computation, no nothing. Just understanding these two concepts and then just breaking it down. And eventually, we found the answer with no, I guess you could say, hesitation. Now, this one right here, actually, when I first saw it, stumped me completely. I wasn't exactly sure what to do. Now, of course, there's definitely the brute force way of approaching it. And I was really tempted to do so. We have 3 to the first power equals 3, 3 to the second power equals 9, 3 to the third power equals 27, 3 to the fourth power equals 81, and 3 to the fifth power equals 243. And then it's asking how many digits are in 3 to the 25th power. Now, I can definitely keep on going. 3 to 6, and then multiply just by 3, and then on and on and on and on until we hit 325. Now, the only thing that really stopped me from doing that, other than the fact that I'm lazy and I kind of don't want to spend my time doing that, is the fact that this fell into the category of being a warm-up. Now, a warm-up is not supposed to be something super complicated where you have to spend a great deal of time trying to figure out. So there must be some trick or some way of thinking that at least is relating to math to get you used to thinking in a more mathematical way, but makes this still at least doable, right? In a very short amount of time, or it's not going to be a warm-up. So let's look at this. The way I approach this is, well, 3 to the first power 1 digit. 3 to the second power, 1 digit. 3 to the third power, 2 digit. 3 to the fourth power, 2 digit. But then more importantly, as I went on and on, I was thinking about it. Every time you're multiplying it by 3, each and every one of these numbers, if you think about it, right? 3 times 3, is it going to cross the threshold of adding another digit? No, not necessarily. It has to do 1, right? 1 multiplication. And then now, when you multiply it by 3 again, then it crosses the threshold. Same thing, right? Here we have 2 digit. If you multiply it by 3, is it going to cross the threshold at this point? It's usually a pretty small 2-digit number. No? So it's again 2 digit. And then the next one's going to cross the threshold. And of course, I went and actually checked 3 to the 6th power. And just think about it this way. If I multiply this by 3, right? Is this going to cross the threshold to become thousands, like the 4 digits? No. So that means 3 to the 6 is going to be 3 digit. Then 3 to the 7 must hit 4 digits, and so on and so forth. So then all of a sudden there's this sort of pattern that you can sort of see. It takes 2 multiplication of 3 to finally increase a digit. So 2 multiplication of 3, finally you have 2 digit. 2 multiplication of 3, you finally have 3 digit. 2 multiplication of 3, you're going to have 4, and so on and so forth. So the best thing to do to sort of guesstimate the answer to this is that, well, if it takes 2 every time, and this is 25, if we divide it by 2, you know, ignore the whole remainder thing, what is it really close to? 12, right? So my guess in this case would be 3 to the 25th. I'm not trying to find the actual answer. I'm just trying to figure out how many digits there are. Just by that reasoning, I would say it's probably about 12 digits. It's a 12-digit number. And if that's true, I'm kind of glad I didn't spend a lot of time multiplying the 3s to finally get to that, right? Because a 12-digit number with multiplication, not fun, I guess you could say, right? And then afterwards, I did check, and then I'm going to leave it to you guys to check it as well. I believe it is 12 digits unless I enter it in the calculator wrong. And if I did, well, shame on me, right? So this is how you would go about solving this particular problem. So at the end of this video, even though math warm-up was a little weird to me in the beginning, I can actually see how it can be kind of useful. So here's the thing. The category of math warm-up, once again, is problems that doesn't require heavy computation, but it does sort of prime your brain, or at least lead you into a specific way of thinking. So notice that each and every one of these problems, the key of it is that it's not heavy in computation. It doesn't require a lot of memorization. It brings you into those sort of logical reasoning and deducting skills, right? The first problem, it looks complicated, but guess what? If I know what the problem's asking, what would answer the question is asking, right? It's quite simple. Understanding the little concepts of what makes it 0, 0 and some number multiplication, and then all of a sudden we have the answer, right? The second one, very similar. As long as we understood the 2 definition concept, right? Just trying to figure out what it's asking and breaking it down and just asking ourselves if this makes sense. Yes, quite simple. And this last one, same thing, right? It seems like a complicated one, but we actually solved it not because we went ahead and figured out the exact number of 3 to the 25th power. But once again, it's just logic and reasoning. It sort of brings our brain into that kind of mode, right, of thinking. So I think actually math warm-up is quite useful. If you're about to do a heavy computation problem, if you're about to go into a math competition or SAT or a test, maybe work on a few problems that would be considered sort of warm-up problems, just to get you into the zone so that when you start taking on harder problems, one that require a lot more thinking, a lot more tedious computation, we'll be ready for it. Thank you for watching this video. See you in the next one.